My name is Cody Duncan. I am a master's student here at DigiPen, and I'm here to show you guys some C++ introspection and reflection using Clang LibTooling. So let's go ahead and skip ahead. All right, so first thing I do want to point out is that we do have some additional sources here. So for example, Austin Brunkhorst, one of the undergrads, has done a very similar project for C++ reflection using the Clang lib tooling for Clang, which is a wrapper around LibTooling, which makes a number of tasks a whole lot easier. It's a great piece of source code to go take a look at. In addition to that, you'll also want to take a look at the documentation for the libast matchers tutorial. It's got a lot about setting up a LibTooling and then a little bit about Clang's AST libraries. Kevin Boos has a great tutorial on doing a full LibTooling example, and Trent Reed has done a number of presentations on reflection that talk about the topic at large. So definitely go look up his resources if you can find them anymore. All right, this clicker doesn't work. Oh, that's important, huh? Boop. There's a power switch. Yeah! All right, so first things first, what is introspection and reflection? Why am I using two terms instead of one? Because oftentimes, I'm sure you guys have heard it as the word meta-reflection, but that's very much a DigiPen term. It's not technically wrong, but it's definitely not the term that you'll find if you try to look it up in C++ nomenclature for the standard and or computer science related papers. So the difference between introspection and reflection is introspection is self-inspection. It is the information about the types inside of your program, about their structure, their variables, which we're going to refer to as fields, their functions, which we're going to refer to as methods, and then the other subtypes that make up that information. It is just structural information. And then reflection is the ability to use and or manipulate this information. So you could even change the structure of a type at runtime. So that is the separation between the two. Meta-reflection is therefore not entirely a wrong term because meta often refers to information about oneself, and then reflection is that ability to operate on it. So I still prefer the more broad terms of introspection and reflection. So what's the utility of knowing about the structure of a program? And so I borrowed a list from Trent Reed because it was fairly complete, but the short version of it is anytime we have to ask ourselves, what sort of things does this type contain? What variables does my class have? And anytime I want to operate on that and do something with it, it's useful to have this information available. So the biggest use case is, of course, generic serialization and deserialization. This is the one most pertinent to game engines by virtue of the fact that if you know the structures of your game objects, of your components, of all of your game-related data, you can effectively write a single loop that will serialize and or deserialize against whatever API you're using, rather than having to do each hand serialization. So then, let's talk about Clang. What is Clang? I'm sure that given that this is a C++ heavy school, you guys are familiar with Clang, so I'll try and skip over a bunch of the more boring details, but it was a project that started back in 2007 at Apple, specifically to create a better tool chain for Objective-C. And the reason why we want to choose Clang as a tool for generating introspective data is because the builders for Clang and the underlying libraries, the low-level virtual machine LLVM, were concerned about this new idea that compilers shouldn't be shipped as just a singular executable that compiles your code and that you can plug into. Compilers should be composed out of parts, and those parts should be usable by other programmers to build their own tools. And so this is where the LLVM framework came about, and they used that to initially build the Objective-C compiler, and then later the C and C++ compiler, Clang. And so we're going to be utilizing a lot of those same base libraries from LLVM and Clang in order to get that introspection data out. Now, big question. We're going to go over a few prerequisites. Number one, does this mean you have to compile your code in Clang? And the answer is no. In fact, we're not going to be effectively compiling the code. We only have to go so far as the tokenization and the parsing part of the project. Once we get the abstract syntax tree out, which is the input into the actual compiler, then that's where we want to stop. That's where we want to pull up all of our information. We don't have to go into the actual compilation process. But it does mean that it has to get past the tokenizer, which means the syntax must be correct. Another prerequisite is that we are going to need all of the LLVM and Clang libraries, which means that you're going to have to compile it yourself. If you see any distributions of Clang that are like, download Clang and try it now, those are more often than not just the executable for Clang as a compiler and then any necessary libraries to just do a compilation. What we need is the whole LLVM framework because we're going to be building on top of that using the same tools that they use to build the compiler itself. So we're going to be doing more, and that compilation process takes a while. And by a while, I mean like 2 hours for release and then 2 hours for debug. So grab your favorite season of Game of Thrones and sit down for a couple of episodes, turn on that build, and then just chill for a while. All right. So let's talk about the 3 kinds of Clang tooling APIs, because Clang wanted to be as flexible as possible for building tools on top of the compiler itself. They came up with different methodologies to do that. The first and foremost of which I do highly suggest, is libclang. This is a C-style interface into the Clang AST libraries, other parts of the Clang parsing libraries, all of the Clang accessible libraries that has been wrapped inside of a C-style interface to make a lot of tasks much, much easier. The particular interface that is most useful for us is the cursors interface. So rather than operating on the abstract syntax tree as the whole tree and writing logic that traverses through the tree, they made a cursors interface that will abstract it into an iteration. And so you get a nice iterator, you just iterate type by type by type. Much easier, nice for loops, much more simple code. Clang plugins is not something that we are going to be overly concerned with because that's really only for plugins that operate on the compilation during compilation. So that means you do have to compile your code in Clang, not something we're doing. And then LibTooling is the underlying library that libclang is built on top of. This is the one we're going to take a look at today. We're going to take a look at the full spec of all the things that Clang is utilizing. That way we can get a nice deep understanding, and that will lend its understanding to libclang. All right, so let's talk about reflection. So for a lot of projects, it may not be necessary to reflect every single thing in the project. And by that I mean usually there are some types that we are very concerned with serializing and deserializing, like networking messages or any data that the program is taking in or out. There's a lot of internal types like certain systems that we don't really care or need to reflect at all. And since we are in C++, I took the approach of taking a look at it from the we are going to get what we pay for. We only want to serialize and or reflect the types we care about and nothing more. And we want to do this as fast as possible. We would like to do this much faster than the compilation process. That way we can guarantee we can get our metadata out faster than taking the entire program to compile, especially for large programs. So what we're looking at here is a little bit of sample source code. So we have a few types over here. Simple enum, A complex, B contained, just to show that we can have another type in here that is reflected. And each one of these is marked up with this reflect macro here. And this reflect macro is going to be borrowing a structure that Clang has as a compiler intrinsic known as an annotation attribute. And so that annotation attribute is nothing more than just a compiler intrinsic that allows information to be attached to a type and then be fed to the compiler for some means in processing. Exactly the sort of thing that we want to do. And so we also have this tucked inside of a nice ifdef, so it's not defined unless generate reflection is in fact defined, because MSVC won't recognize this attribute intrinsic. So when we are compiling our code in MSVC, we want to get rid of that and just make it a blank statement. Another part of the structure here is a reflected headers H and CPP file. And this is the idea that we have a single CPP file that we want to run our reflecting process on. And so by that single CPP file includes just a header, and then that header includes to all the other headers that have any types that are reflected. And the reason for doing it this way is effectively we're setting up for Clang's parser and Clang's tokenizer a unity build. It now doesn't have to go through all of the redundant check for includes and take out anything marked with pragma once or anything that's guarded by header guards. It can include all of that in one big file and then begin tokenizing it. This speeds up this process, yay, up to 50%. And so since we're only doing the headers that we care about, we're also cutting out any extra headers, speeding it up further. So this is to try and guarantee that the process of building our metadata is as fast as possible, and that we're only doing it on types that we care about. So let's talk about LibTooling. So now that we have our markup ready, what we want to do is we want to run effectively the Clang compiler. And now onto this Clang compiler, we want to attach a front-end action. And luckily, the LibTooling API gives us a very easy way to do that. The three pieces we need are a common options parser, a Clang tool, and a new front-end action factory with some custom logic type that we have specified here as a template argument. So this particular part, not hard. We just pass in the arguments to the program into the common options parser, build a Clang tool, and then have the tool run a new front-end action. We'll get to this part in just a minute. Really quick, I do want to talk about the common options parser. Particularly because the common options parser has two parts. It has the part where it takes any arguments pertinent to the tool, and then it has the part where it takes arguments that are pertinent to the compilation. Clang tools are built on top of the compiler, and so as a result, they need a lot of the same information that a compiler does. Normally, what Clang tools will do is, if it's Clang compiling it, it will spit out a JSON file that has all of the necessary compilation information, include directories, any macros that have been defined, any extra CPP or OBJ files that it needs to bring in, all of the command line arguments that you would send to the compiler. It will stick this in a JSON file, and then the Clang tool will load it up. Now, since we're compiling ours in MSVC, and because we're doing a particularly special compilation on a single CPP file that's not the same compilation as the project, we will not have that JSON file, and so we effectively have to define our own, but we can do that just by virtue of the arguments that we send into the common options parser. And so what we would do is we would send in our own command line, and it would look something like this, broken up. We, of course, have our executable, which is our tool that we're building. We have the CPP file with all the includes to all the types we want to reflect. Then we have this double dash operator to note we are separating off to anything that we are specifying as compiler arguments. We are going to define our generate reflection macro, specify that we're compiling in C++, and finally, include any necessary include directories to make this compilation work. So now, let's take a look at that underlying class I was talking about before. In this case, it is decal finding action. This is the specific class for the project that I built, but it would go as this argument here, this template argument to the new front-end action factory instead of Clang syntax only action. That one works as a really good example. So this decal finding action is an AST front-end action. And it doesn't do very much. All it is going to be creating an AST consumer. And so we have this build an AST consumer and pass in another piece, another type that is our own custom logic, in this case a decal finder. But you'll notice that it's past the source manager. This is going to get fed further down. So now we're in the decal finder, which is an AST consumer, and it doesn't do much. The AST consumer is an interface. You can overload a lot of different functions, but for the one we're concerned about, we really only need handle translation unit. So this is the first part of the Clang API that we are implementing to hook into Clang's front-end action library for LibTooling. And all we really need here is we're passed in this AST context. We're going to pass that down to our visitor, and we need to get the translation unit that we care about. And we're going to call traverse decal on this. Decal visitor is another custom type subclassed off of another Clang LibTooling type. So let's go ahead and take a look at that visitor, specifically traverse decal. Yeah. Oh wait, nope, this is the type first, sorry. So this one is a recursive AST visitor. This is the part where the magic really happens. What it means by recursive AST visitor is, I probably said a few times already, abstract syntax tree. For those of you not familiar with compilers, an abstract syntax tree is a tree that is built after the parser that simply defines the structure of the program in terms of its abstract types. So for example, if my program consisted of nothing but 2 plus 2, an abstract syntax tree would see that as int, binary plus operator, int. This would be structured as a tree where the binary plus operator is at the root and the two ints are leaves. But of course, we have much more complicated stuff than that. So the root is essentially the translation unit. The branches off of all of that are going to be our class types. The branches off of those are going to be fields and methods. The branches off of those are probably going to be even more types. And it continues down until you get to leaf types, which are often just primitives like int and float and so forth. But this is going to be the object that is going to be doing the traversal down and across the tree. In this case, it takes the approach of a depth-first traversal. But you can change its behavior just a little bit. So really what this guy is going to do is go across that first layer of branches across all types, and then those are going to depth-first traversal in our own logic. So the important bits here really are traverse decal, which is a function that we're implementing off of the interface for recursive AST visitor. Statement and type are also things you can implement, but I've just put them here for demonstration. Get decal location is important because if you ever need to get out the particular CPP file that a type is contained within, then that's the sort of thing that you'll need, this Clang source location and then some logic in order to get it out, often as a string. And then print decal here is just for debugging purposes, because if we're running a command line tool, it's useful to have it spit out what the heck it's doing. All right, so let's dive into that traverse declaration. So this guy isn't particularly complex at the top level. This is the lowest level of the LibTooling API that we have to build in order to hook in and get information out of the AST. And so what we're doing is we have this custom function here, LLVM2Reflection, which is going to be doing a lot of custom logic on this declaration. And then this bit right here is just for debugging purposes, to print out that declaration and show it to the command line console. And then finally, the last step is to pass it up to the base types function so that it will traverse to the following branch, which will then call this function again. So taking a look at our generate type here. Also pretty simple. First thing that we want to know once we have our declaration is this declaration reflected? Does it have that annotation attribute on top of it? If it doesn't, we can just totally skip it and go on. If it is reflected, then we want to check and see, will this dynamic cast is a check. It will return null if it can't cast. It's going to check and see, is this a CXX or C++ record declaration? If it is, we're going to go ahead and scrape that type, get its metadata. Otherwise, we're going to check and see if it's an enum. Having enums scraped is super, super handy, because then you can also build a table of strings for your enums for any debug printing. So let's take a look at this isReflected function. So now we're getting into a bit of the nitty-gritty with the AST functions. It's not particularly hard logic, because all we're doing is we've been passed in this declaration. From this declaration, what we're really concerned about is, can we get the attributes out? Iterate over the attributes, find any of whom are an annotation attribute, grab their annotation, and then check and see if the string matches. If it does, we have in fact a type that we've marked up as reflected. If not, we skip it and return false. So not particularly hard logic here. But one thing I do want to mention is that annotation attribute is really powerful because it accepts a string, which means you can pass in stringly typed information. And we'll see an application of this later. But for now, we're really just concerned about, does this string, the word reflect, exist in here? So backing up, after isReflected, we check and see if it's a C++ record decal. And if it is, we're going to go ahead and scrape it. So let's take a look at that function. So the first thing that we always want to check when scraping a type is, do we already have the metadata for this type? Have we already defined this type? Because there's no reason to do this twice. But you're going to hit this a lot, because the abstract syntax tree is a tree of those types, but they point elsewhere to different tables for their information. And as you can imagine, you might have multiple types that contain, say, a matrix class or a vector2 class. And so if you end up with those, you have no good reason to reflect vector2 twice. So we can go ahead and skip anything that we've already reflected. And then we're going to move on to doing, well, grabbing the fields and the methods. The way that I've set this up here is sort of as a depth-first evaluation. So instead of taking the metadata specifically of that type, I'm going to take all the pieces of the parts that compose it. I'm going to take the fields and the variables first, and then I'll build the type and add the fields and variables to it later. I can hook them up using some opaque handles. You can do it the other way around. You can build the type first and then add the fields and methods in from under it. You're already guaranteed at this point that the types are going to exist and be valid. Second half of this function is quite simply, we've already scraped all of our fields, we've scraped all of our methods, and we go ahead and construct this type. We get a type back. And so then we're going to do the hookups, which are these add functions here, passing in the types, opaque handle, and the field, type getting the method, hooking up methods to its parameters. So not particularly hard logic here, which is the really nice thing about taking this approach. If you understand C++ well enough, and if you've seen some of the logic for pulling this information out, the actual process isn't hard. So we're going to take a look at under the hood of this add type function right here. Under the hood, I'm having it call this function, which is add new type from Clang cx record decal. Probably the longest named function in this entire project. And you'll see that getting the important information out here isn't particularly hard. A lot of the stuff that you really want is defined on these declarations. One of the pieces that you want that isn't defined is probably the size of this structure, which is defined only by the AST record layout, which we get from the AST context. So if we back up a few slides, yeah, right here. No, wait, one step further back. Yeah. We're calling this generate type and passing in a context that we got from further up the chain in the LibTooling stuff. We got past the context, I think, one level before. Yeah, the set context function set that context. To mContext, we're passing that in. And then from here, oh, we're not actually using that argument. I must be setting it somewhere else. But regardless, we are going to need that context passed in one way or another. So when we get it down here, we can use it to get the size of the struct out, because only that layout, that AST record layout table knows the size of the whole size of all the structs. And then the rest of the information is pretty easy. We just get a string. We have the length. We know it's a composite because it's not a primitive. It's not an int. It's made up of a bunch of things. And also, we just ask, is it a struct? Because if it's not a struct, it's a class. There are other records that we're going to do some scraping on. And I've put these examples here, like field declarations, method declarations, parameter variable declarations, enums, functions, variables. So I'm going to take a moment to look at the high level of the next scraping function, which is going to be pulling out the information necessary to get a hold of all of the fields information. And I want to point out that right here we're looking at about 60 lines of code. And so doing it via LibTooling, you get a lot of the under the hood functions because you have to go reference something from another table or convert it to a different library type in order to get the information you want out. The nice thing about libclang is that this particular section gets shortened to from 60 lines to on the order of like 30, maybe 20 lines because of the abstractions that they apply. So just another argument for why it's easier to do it that way, but you don't get to see all the nice bits under the hood. So at this point, I've been talking for, 25 minutes. So I'd like to go ahead and take just like a 2-minute break for you guys to stretch, because it's kind of late in the day, before we dive into this particular function. And if anybody has any questions they want to ask, they can feel free. Otherwise, feel free to go get a drink or something. Yes? Common options parser?
Common options parser, yeah. I didn't see any logic in the Clang source for passing along those defines. Does it actually do that and define -d stuff, or do you have to catch that later and define them?
So in particular, the common options parser is really just designed to take in the array of string args and the number of string args that are passed into the main function. It does do some operations on them, because if you pass them in and they're invalid, it will go ahead and spit an error out at you and then abort the rest of the program.
Right, but okay, so whenever I looked at the source code for it, anything after the --, it's like custom arguments, so it doesn't care about those. So those are your arguments for your particular program. But if you had -d something, I didn't see any logic, or at least couldn't find that logic to where it takes those and adds a macro definition to the compiler instance. So does it actually do that, or?
It will. After that dash dash is not just custom arguments, but also any compiler arguments that are compatible with the Clang compiler. That dash D syntax is, of course, like the macro definition that they borrowed from GNU. And so under the hood, it is writing the logic to suss out what all of these arguments are as if it were going to pass it into a compiler. And if you want, you can write that logic yourself instead of having a common options parser. So you can actually construct your own instance of the compiler, stick your front-end action onto it, and then pass in all of those arguments not as a string argument, but as the actual internal types that they have. But when I did it, it was about like 150 lines of code, and some parts of it weren't particularly pretty. The Clang tool is nice because it automates that whole process into a few lines, but you still have to deal with that. You still have to deal with what compiler arguments you're passing in, and so you have to have a little bit of glue code putting those into a nice string for it. All right, any other questions? All right, I'm going to stretch for a sec. Because I noticed there was just a couple people that look like they've had a long day. Yes?
What is introspection?
Oh. I had a whole slide on that, but maybe I was not entirely clear on that. So introspection is if you look at the idea of having reflection information for a program as being two parts. One part being the information that defines the types themselves. Like, what can you ask about a type? How big is the type? What variables does that type contain? What methods does that type contain? Is there any metadata on that type that we know about? Is that type a subclass of something? All these questions, if we can turn that into data, then introspection is the process of building that data. Whereas then reflection is different by virtue of the fact it is focused around utilizing or manipulating that data. So for example, if we wanted to change the size of a struct, like you can do in JavaScript by getting rid of or adding variables, then that would effectively be reflection. Otherwise, if you wanted to set a value on a struct, like if it had an integer inside and you knew the name of the integer, but you didn't know anything else about the type, but you had the reflection information, then you could write a function that writes into that integer without accessing that integer directly. So that process is reflection, just what can you do with this information? And how can you manipulate it or change it? Does that answer, or we need some different detail? All right, perfect. Yeah. All right. Yeah.
Are you going to share these slides?
Oh, yes. I'll get these posted to Facebook right after the presentation. I'll give you guys a link directly to the OneDrive, and you can download them yourself or take a direct look at them. Also, if you guys have any questions, feel free to email me. I'll also post my email address with that post on the Facebook event page. So you guys can be like, hey, Cody, your stuff's stupid. Explain it better. All right. Clock's got a bit of glare, but we still got like another minute. All right. Looks like our remaining combatants are back. So, if you guys are ready to continue. Go ahead and raise your hand. All right, good. All right, so let's get into this scraping field function. This is the one where we have some of the most, I need to get some information out, where the heck do I find it, kind of questions. So we're passing in a field declaration, so we already know that this declaration is about a field. That's super handy. Out from that field, we're going to be grabbing the qualified type. And by qualified, I mean a primitive type by itself would just be an integer. But you might add on the qualifiers of constness, or it's a pointer, or it's a reference. So the qualified type has all of those extra pieces of information around just a primitive or a composite type. Then this next line here, field qual type dot get as string. I just have that there for debugging purposes, so I can see, put a breakpoint there and see at the top of the function what kind of type that I happen to be dealing with. The following line is going to go ahead and get out the Clang type under the hood, and that's going to be the qualifier with or the qualified type with all the qualifiers removed. So just the type that we really, really care about. We can ask for the qualifiers later. So then the other thing we're going to do is we're going to try and cast this to a C++ record declaration. If this function returns null, it is not a struct or a class. If it doesn't return null, then we're looking at a type that we potentially have not scraped yet. And so we're going to go ahead and take a moment to jump off to that other function and scrape that type first. That way we know about the existence and structure of that type before we continue on with this field. Also, that gives us the ID for that type, and how we're going to get that is I have this add type function set up so that if it's passed a type that it already knows about, it just returns a reference to the data that we already know. So a lot of the times this is going to be just a go get me this thing in our type information. So then we're going to construct our field, zero it out, followed by assign that ID of the type, so that opaque handle, so the field knows what type it is, followed then by getting its name, and we're going to set its owner type to invalid, because we haven't actually, since we're doing depth first, we haven't actually defined who owns this field yet, so we're going to go ahead and make sure that we put it to something that is going to yell later if it's never been filled out. So now at this point, it knows its name, it knows what type it is, it doesn't know who owns it, but we'll get to that. And now we're going to start answering some of the interesting questions. Is it a pointer? Set it to true. Type, get canonical type internal, is quants qualified. Finding that function was a little bit fun just because I had to figure out I had to go through this guy. So from there, we know it happens to be a const field. Is it an array? And in this case, we got to try and cast it to a constant array type. If that works, then we go ahead and pull out the size of the array. In other words, another number of elements that it can contain. Tuck that away. If it's not an array, be sure to set that to false and the number of elements to 0. And then finally, we want to pull out the byte offset. This is probably one of the most important pieces of information for serialization. Because if I have just a block of data, just an array of bytes, and I know the structure of this array of bytes, like I know that there is an integer at the 4th byte, then I don't actually have to have a pointer to that type. I can have just a void pointer or a pointer just to that data somewhere and be able to operate on it as if it were a reference directly to that type. That's what we want to do with generic serialization. We want to be able to hand in any reference to memory that represents that type, and then the structure of that type, and then be able to read in information and fill that out without having to write a bunch of functions that take a bunch of different types to serialize them. So we build that field, backing up just a bit. Once that field has been built, that was called from the scrape field decal, gets added into this field array. This field array gets hooked up with its parent type. So this is where we filled out that M owner type, is right here. And then after all of that processing is done, now we've gathered information about the type itself, all of the fields that it contains. We've scraped any types that those fields are that we don't know about yet. That traverses the entirety of the tree for the field and type structure. And I'll leave it to you guys to take a look at methods and parameters, because much of that source is the same, because a lot of it is just operating on types and then a few extra function-y bits. So moving forward, after we've built all of this information, after we've pulled out all the stuff that we want to know about, we have to do something with it, because we want the program that we're gathering this information about to be able to do something with it. And so we have our AST consumer, which was that custom logic we were just looking at. It's going to feed that into some reflection storage. And then following that, we're going to turn that storage into a binary file output. So once we're done, we have this file, which contains all the metadata that defines all the reflected structures of our program. That means that the program itself, after it's been compiled, can then load up that binary file and know about its own structures. That's cool. This reflection storage is probably one of the most important parts of this whole bit, by virtue of the fact that it's where we're putting all this metadata. And it's important to be able to both fill it out when building the metadata and then fill it out when loading it back from the binary file output. So that's right. Oh, that goes into project setup. OK. So we'll get to talking a little bit more about some suggestions for this reflection storage in a bit. The other important bit is, of course, project setup. Oftentimes, you want to have a reflection-based library, which contains that custom code we were just looking at for scraping all of the information using a Clang libtool. It's also going to want to contain the definition of that storage structure. And then we want to have a deserializer here, particularly just reading that binary file out. Now, that does two things for us. Number one, that means that anybody else who is consuming this base library, if they have that metadata file, can consume it. And number two, by definition of that deserializer, you're defining the format of what that binary file should look like for anybody who is trying to build the reflection processing executable itself. So then, of course, we have the reflection executable, the tool. That's going to build this reflection data, which is going to be consumed by our application. Couple more projects that are super useful to have. Number one, a sandbox. So just a program that loads up your reflection data and that you can just toy around with to take a look at, OK, I have all the types I was looking for. This syntax is working. Anything for just a nice, clean environment to try things out in case you have some bugs with the reflection itself. And by the same token, a unit test library is super handy, because a lot of times a mistake in one type turns into a mistake in all of the other types by virtue of writing it out to a binary file. So what you want to do for those unit tests is have the reflection tool run, spit out a binary file, load it back, and then run unit tests to validate that information is correct. Because if you're off by just 1 byte, then you'll probably get all of your unit tests to fail. But you have these nice tests to tell you exactly where it failed. And if it gets more complicated than that, you can always go back to the sandbox. So as for the storage structure of the metadata itself, there's two ways you could do it. You could do it as a reflection of the types themselves. So you have a type class that contains methods, which contains parameters, and the type class also contains fields. Or the way that I suggest it be done is as a tabular format. And the reason for this is that we can still get this structure by using some opaque handles. And what I mean by opaque handles is just IDs. If I make a new type and it's the first type I've scraped, I'm going to give it an ID of 1. Second type gets an ID of 2. And so now, as long as these are in an array that is indexed, I can reference them as long as I know which ID they belong to. And so you can still hook up this kind of structure, but having it in this nice tabular format does a lot for you in terms of the kind of tools that you can build. Say, for example, you wanted to build some IntelliSense into some source code editor for your engine, because you're getting super fancy like that. And you wanted the user to be able to ask, do we have a method that starts with banana? You probably don't want to have to iterate over all of the types and then go through each array of methods one at a time. It's probably easier just to iterate over all the methods at once and check their names. There's a lot of different tooling cases where having direct access to a specific kind of type is really useful information. So that's why I suggest this particular structure. In addition to that, it's also much easier to serialize this structure, because that means that if you're looking at the binary file and you know you're probably in the fields array, you know how big every field should be, how much information you've stored for each of those. And so if you find the name of one field, you know now where the next field should start in terms of a byte offset. Instead of this, which can vary wildly because you don't know how many methods, parameters, and fields it's going to contain. So that's why I highly suggest this kind of a format and then forming this structure by virtue of opaque handles. Another cool thing you can do with opaque handles is if we have this reflection storage in the middle of our application, and if we have set it to some really nice global variable that anything can access, that includes Visual Studio's debugger. And so what we're seeing here is a NatVis file that is pulling open reflection internal reflection processor, which is the type that I was using for storage. And then it's pulling out its type list. And given that it's an STD vector in Visual Studio 2015, to get a pointer to the first element, my pair, my val2, my first, plus the index, which is the type ID. Because we happen to be looking at a reflection type ID. And so that means when I breakpoint into the middle of my program and I happen to have a type, I can open up that type, take a look at its type ID, and the NatVis file has already filled out the ID and the name of that type for me by going and referencing that global variable. That is super freaking handy, because if you're asking for some type and you get a different type than you expected out, you get an immediate verification of this instead of having to go look up, oh man, it's ID 11, so I got to go find that object somewhere else, open up the array, find ID 11. You can set that up in the debugger for you. It's super nice when debugging both the reflection processor and any tools that you build off of it. In addition to that, going on to advanced features, a kind of syntax that we want to support for the one consuming the library is, up to this point, we only have string names for these types. We have a whole list of types. They all know what their string name is. And so if we wanted to pull one out, we'd have to compare strings. But of course, being in C++, we really like type safety. Type safety is our bread and butter. And so if we can support that, all the better. And we can, because this reflection processor is running before runtime. It's compiling the program. It should know what all of the types are. And so therefore, we have as much information as the compiler does about what types exist. We should be able to do some form of type checking. And so we're going to get this done by doing a little bit of source generation. And it's not particularly hard source generation either. So after spitting out our metadata binary file, we'll call a little bit of source generation. And it's going to look a little something like this. We have this type container here, which is a templated class on type T. And all it does is contain a type ID and a pointer to that type, just to make referencing it faster. And so once we generate that header, we can generate a CPP file, which then, since we know all of our types, we just iterate over all of our types and spit out a type container. Type ID is whatever its ID is. Type container ID data is whatever we've been passed in for this function. Call get type, grab that ID, hook that pointer up. And now you'll notice that these are static variables on a templated type. So anybody that calls type container float in the consuming program after this function has been run is going to be able to ask directly for this ID. We have now matched the type to its ID. And as a result, we can support this kind of a syntax, this get type, grab an int, and not even have to do a string comparison. So we've made it more efficient, we've made it type safe, and the cost of generating this source code is really small. So fantastic work. Let's see. Oh yeah, this is the close-up of the type container definition, and here is the close-up of the generated source code, in case anybody couldn't see from the back. So let's talk about the utility. One of the big reasons why we are building all this information and making it accessible to the consuming program. So here's a nice function, a serialized type function. What it's doing is it's passing in that storage type. In this case, it's called reflection data. It's passing in a reference to the type that we know we're trying to serialize via its metadata. And we're passing in a void pointer to the data we're trying to serialize. And finally, we're passing in a JSON object that we want to spit back out, the serialized object. And as you can see, this logic isn't particularly hard. It's a for loop over all of the fields. It's going to grab the field out, it's going to find its name, it's going to figure out its type, do a nice switch statement for all the primitive types that we can actually serialize directly to JSON. And then here we have this byte offset again. Since we know the byte offset, we know exactly where to pull it out of that void pointer, since we know the structure. And then we're going to go ahead and stick it into this, assign it to this out JSON data. And let me see, where do I have the other part of this? Yeah, that's right. And if it happens that one of the types that we are serializing is in fact not a primitive type, then we just make a recursive call, pass in another JSON object, and then assign that JSON object into the object we were serializing, and we're done. And this works for all types that you've reflected. So now this is the entirety of your serialization, and then something similar for your deserialization code, all in approximately 70 lines of code, and you never have to hand serialize anything again. Nice. So let's talk about more advanced features. Tag metadata. Anybody here who's used C# or Java knows that intrinsically to these languages, they have attributes that you can put on functions or variables or on types. And we even saw a little bit of that with that annotation attribute that Clang supports. And so we want to support our own customs ones. And so this is the work that was done by Austin Brunkhorst. Part of the reason why I suggest going and looking at his work is because he's set it up so that you can subclass this meta property to a slider. Slider has some constructor that it supports to pass in information that you care about for a slider. And then this information can be applied to some field. The same is also true of this range here. So with a range and slider together, you know this object can be adjusted by a slider, and it can have a range of 0 to 1. That is super, super nice for anybody trying to build UI. And really this follows the question of I'm asking questions about the structure of the data and how I can modify it. So this is reflection incarnate. And then here's some source code for then how you would suss out that particular metadata. Just some sample high-level stuff. But the construction of setting up that metadata isn't hard. If you guys remember the annotation attribute from before, it can store a string. And so literally what this is doing is everything between this parenthesis for the meta macro to this end parenthesis is being tucked inside that string. And then during the source code generation phase, it's generating a function that spits this string back out as something to assign to the type or field with that particular ID. Which then, since this is generated as source code for the consuming application knows what the definition of range and slider is. But up to this far, the reflection processor itself has only ever known this as just string information. That's kind of a cool workaround to use stringly typed information. So the construction there is not particularly hard. Let's talk about more advanced features. So here we have some more work done by Austin Brunkhorst, reflected function invocation. So the other fun thing with reflection is if you know about the structure of a program, you probably also know about the methods that a type supports. And what you'd really, really want to do is be able to invoke a method on a type without using a function indirection. Maybe you want to tell it like the particular name of a function you want to call. At that point, we're getting into scripting. And so in order to support that, we can do that with a little more source code generation, and it's not particularly hard. In fact, the method that Austin used was a generated wrapper function that is really just a lambda function. So reading in the metadata for that method, he just sussed out, okay, this is the type that I have a method for. These are all the parameters that this type supports. So I'm going to generate this wrapper function, pass in a variant for the type that the method is on, pass in a generic variant argument list for all the args that could be passed in. We already know what type it's on, so we can just make a direct cast. We already know what the arguments are, so we can just make another direct cast. And what we're effectively looking at here is a function that would be generated the same way that a variadic template would, except fully expanded rather than just expecting the compiler to take care of it. That's really nice because if you're executing this function, you can now see every single operation that occurs rather than it being hidden behind the abstraction that is variadic templates. So if you ever have to fix a bug that happens to be in that source code generation, super easy. And then by the same token, this is all type safe. That's fantastic. So now we're supporting like scripting style function invocation. It's type safe, it's easy to debug, and the source code generation for it is not something particularly hard. Let's talk about more advanced features. Let's talk about probably the most advanced features, or where the edge of the field of metadata is today. There's an interesting question that comes about in large projects, and I mean like really incredibly large projects where you have a bunch of parallel processes that are trading information between each other. For the sake of argument, we're going to talk about like an engine and then a tool that is connected to that engine for editing content in the engine via the network. Since it is network connected, it's going to serialize messages across and any other type information. And if the project gets big enough, or if one part of the project gets behind enough, then you can end up with this really interesting wonky situation. Let's say, for example, I have myself as a tool implementer, and I have my engine buddy, and my engine buddy is getting way ahead because I'm taking forever to write some new feature in a tool, and my tool is horribly, horribly broken. And so my designer is using an old version of the tool with a new version of the engine. And let's say that Engine Buddy has added in an integer to my type. So now, if we try to serialize that over the network and I receive it inside of my tool, I run into a bit of a problem by virtue of the fact that I can compare the type that it says it is with the type that I think it is and see that the sizes are different. So already I'm raising a red flag because it's like, oh, the size is different. I must have gotten a different type. But you and I know, we can see that this really is just this type, but with one extra variable. That's not bad. And in fact, since this extra variable came out of the engine, and the tool probably doesn't support it yet, so the tool doesn't even have to care about that extra variable. And so if we can know that the structure has changed, then we can acclimate to this new information. And so that's where we get into metadata versioning. If you run the reflection processor a second time, and it compares against the original metadata and says, oh, something changed, it can store a delta between what changed, in this case, plus one variable. And so then, if the engine and the tool communicate and say, oh, hey, I have one extra variable, here's the delta up to this version. And since the tool can know about that, the tool can say, okay, when I get this type, I know I have to remove that variable and then forward it along. And if I try to send this type back, I have to put back in information for that extra variable. So it can version up and down as long as both processes are aware of the delta between them. And so at this point, your designer is no longer blocked. The network is going to handle versioning that information up and down. And as a result, the designer can use a very old tool with a very new engine and not have to wait until somebody builds a new metadata file. Now, I know many of you are thinking that for the size of many projects, building a new metadata file is not particularly difficult. But like I said, the syntax has to be correct in order for the metadata file to be parsed. If you have a super, super, super large project, building that file may be a very expensive process. It may be something that takes a few hours. And so maybe you just don't have the time to do it. Or some other things can make it difficult to get a new metadata file out. So for example, if it's difficult to update that tool, perhaps your designer works on the other side of the earth or something. So in this case, when you need that extra robustness, when you expect that these processes are going to get out of sync for the metadata that they're using to serialize their types, then adding in some metadata versioning can build the robustness higher, make it so that they can keep operating even under uncertainty. All right. So I don't have any more advanced features than that. So we're at the end of the presentation here. So Q&A session, but I've already been talking for about an hour now. But before I let you give you guys an open floor for questions, I do want to answer one extra question, which was, why didn't I go into more detail about the structure of setting up that reflection storage object? And it's quite simply because it really was better explained by this diagram, where it's really just arrays of information. if you guys think about it very carefully, this is not too dissimilar from components in an engine, where you just store arrays of components and you hook them together by using some similar ID. So I know you guys can already handle that kind of information, so I didn't want to bore you with the semantics of that particular structure. And then at the same time, I could have gone into more detail on the API regarding functions like field declaration getName, but the Clang documentation for their AST library and for their LibTooling library is fantastic. So I'm not too worried about you guys being able to get this information out. Plus, if you're doing it with libclang, it gets even easier. So, and on a final note, I do highly suggest taking a look at the other projects that I mentioned at the beginning, so particularly Austin Brunkhorst's project and or the other two tutorials I pointed out. They have a great deal of information and a great deal of even some foundational tricks that are interesting to learn from. So I can highly suggest learning from those, not only for doing introspection and reflection, but for other things as well. All right, so that's all I got. Who's got questions? All right, let's start over here.
So you're using byte offsets for structures that you found through Clang. Do you see any potential issues with different intrinsics between your source code compiler, so the compiler that you're using to actually compile your project, and then libclang? So like, I guess offsets not being the same or deterministic?
Yeah, so there are some issues with that, but for most primitive types at this point, a lot of the compilers are focused toward a singular standard for how big these types should be. Back in the day, different compilers would have different sizes for primitive types. So for example, your int could be 2 bytes or 4 bytes or whatever. But nowadays, it's pretty well standardized for either 32 or 64-bit systems. And by the same token, Clang under the hood is going to be aware, you can set it to different settings for either a Microsoft-compatible build or for a Unix-compatible build or different platforms. And so as a result of that, Clang trying to support everybody because everybody's pouring money into it, you can turn on a few compiler flags that will make it compatible specifically with your code, and it will try to mimic those type structures as closely as possible. And they've done an excellent job. I mean, for example, Visual Studio 2015 Update 1 added in a native Clang compiler to Visual Studio, and then Update 2 improved on it with a Microsoft Code Gen backend. So already you can just hit a drop down and switch from the MSVC compiler to a Clang compiler and compile the exact same source code, which is
Essentially, right, there's two, right, with the bytecode languages, essentially they output for LLVM, and then Microsoft has got two tools. And that's the difference really between compilers architecturally. So I mean, like, what Microsoft is doing is like Update 2, which is probably not super duper stable, but you can actually use Clang as your primary actually parser, and then it will just, you know, generate this Microsoft bytecode that you probably read. Oh, nice. Yeah, no, that's cool because you're probably doing all the awesome stuff. But, yeah, I would say if you're never making updates to Visual Studio.
So thank you for pointing that out. I wasn't entirely aware of that, but I'm going to repeat it just for the camera. So what this fellow has mentioned is that the compiler for MSVC and Clang output a particular bytecode, and all that the compiler flag is doing is switching between different bytecodes for then a code gen backend to be able to consume. And that is really what the structure of the program is being defined by. Did I get that right? Okay, thanks.
Yeah, totally.
All right, we have one more question. Yeah.
Yes, you mentioned how you could feed the compiler function, compile introspection data back to Visual Studio, so the debugger.
Oh yeah. Boop, 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 boop. Yeah.
Is it kind of impossible with other with other text editors like Sublime or so on? Like if you were doing like your own scripting language and you like compile the types of tabs and all the fields and so on, and feed it back to the
I imagine that you can. The amount of work that it requires depends on the structure for the setup of that particular debugger. So the nice thing about the MSVC debugger is that it can do arbitrary execution. So you can open up a command window, call a function, and then it will execute immediately based off of that binary by looking up the function pointer and then trying to execute that piece of code. And so then NatViz just really is taking advantage of that by saying, okay, I'm going to process this as an immediate execution and try to get this object out, do a little pointer arithmetic, and grab this particular STD string. For any debuggers that are that really have to know all of the information up front where they can't do an arbitrary execution, then you could feed in that metadata to the debugger and then like expand it back out into its consumable format to where it can know, okay, if I have a type ID and that type ID contains an index of 1, then go ahead and replace it with this name value to feed into it. So for any debuggers that can support that kind of thing, that's also possible, but it's more work because now you have to write a program that outputs it to the consumable format for that debugger. So regardless, there's some work you can do. There's some other cool things you can do with being able to debug this just because the information, once it's built, is relatively simple to parse through.
Can I make an addition to that? It's actually like a really cool idea because Unity, right? The Unity tools for Visual Studio is like their primary tooling there. Unity is now shipping a debugger extension for VS Code, which is cross-platform. Essentially, it's a IDE that's sort of Diet Code for Visual Studio. So if you have like a game or something you want to like write, you know, say if you're like, let's just say that you're doing the IntelliSense option, right, or you're doing the auto-completion option. Essentially, if you don't want to write the actual debugger structure or like the GUI, like what Unity is doing is they're deploying like essentially, you know, sort of a TypeScript-y, JSON-y, right, JavaScript-y type extension to like this one existing platform. So like you can essentially run Unity and you don't need to install Visual Studio. It doesn't need to be on Windows.
Oh, that's cool.
Yeah, and it's like it is written by the Visual Studio team. It's written in TypeScript, which is essentially C# with JavaScript, right?
Yeah.
And so you know you can type like you can probably bake an extension like with your engine information and then just get that and attach that debugger to your game and debug your script, right? Probably using like the information that you want from your. If that makes sense. I mean, it's kind of like it's kind of what you're missing, or something similar to that. This is sort of
Yeah.
That's like a lot more of an independent project. Probably as complicated as writing your own IDE itself.
So I'm going to just repeat for the camera. The smart fellow again has mentioned that there is a plugin for Unity to be able to take in information like a Visual Studio Lite. And so,
It's an independent product. It's
oh, sorry, an independent product.
Yeah, it's code.visualstudio.com.
Code.visualstudio.com. And so you could take this metadata information, output that as a consumable format for that particular tool, and have that available for Unity builds. And I mean Unity the engine, not Unity builds like building one CPP file with everything included. Another cool thing, just as a quick note, because it's a pretty neat new feature of Visual Studio 2015. If you're not familiar with NatViz, it really is just this XML format that can do arbitrary execution for making your debugger look much nicer when it's examining a type. Cool feature of NatViz in 2015 that they changed is now if your NatViz is inside of your project, and if you modify it while the project is running, it reloads the NatViz and then changes the output here immediately. So now you don't have to go through and change any regex settings, or not regex, regedit settings, or you don't have to like completely restart Visual Studio to get it to reload that file. You can just start editing that NatViz on the fly and see your debug output change here. It's fantastic for for iterating on this debug output. It sped it up how long it would take me by at least an order of magnitude. So sweet feature, definitely try it.
So one thing kind of.
Oh, hold on. If anybody since we're already over time, if anybody needs to leave, feel free. We're going to get this video posted up later, so you can catch any of the remaining questions if you need to head out. Because I saw a couple guys getting up. Okay, sorry.
This is kind of specific to the internals of like the parsing tool or whatever, but one thing that I ran into with using LibClang was resolving the system header includes for the compiler, because with LibClang it doesn't provide like a default Clang system includes like for standard types. So what I had to do was just include the MSVC headers for the project when I was building it, and I noticed that you didn't do anything in the LibTooling part. Is that done automatically?
You're correct. It is not done automatically. So looking back over here toward the common options parser. So you would have to include it here as an include directory argument into the compiler, because you have to meet whatever standards are necessary in order to get that code to compile. And I'm trying to think, there was one other thing about that. The other thing is that if you're trying to compile with the Microsoft headers, you're going to need the FMS compatibility and FMS extensions compiler flags in order to be able to compile those headers. But it does work now.
Oh, it works.
Yeah.
Oh, thank God.
I think that was their big push for C2, or at least for the project that I used, it worked.
And there was another, I don't know how far this is, like a long time ago, as like part of an effort to get it to the point where it could actually parse, like say, Windows 8, because before Clang was like, there was just no way. I believe there was a tool that spun up that you can feed Clang CL, like CL arguments, like you could feed it the exact thing that you feed to CL, and it will translate it into the Clang command line arguments, basically. So it's like command line argument interpreter. I don't know like how because the compiler for Visual Studio has been moving like at a very like high rate of speed, but you don't generally get new compiler flags. So the way that CL has been called is pretty static, and so presumably like if that's even been around, you could probably like unify both how you're approaching compiling that thing by just passing it, even the way that like whatever your final output called a CL is, which is VC bugs somewhere.
Yeah, I remember having to experiment with Clang CL. That was a particularly fantastic executable.
Yeah.
So to repeat for the camera, what he was talking about was before Clang really did a push toward making itself compatible with the Microsoft standard libraries, there was an executable that wrapped the Clang compiler called Clang CL, CL being the name for the MSVC compiler. And so this particular executable, its whole purpose in life was to take Microsoft arguments, Microsoft compiler arguments, convert those into Clang arguments, and then compile it using the Clang compiler under the hood. So again, this is the flexibility of having all the libraries that build the Clang compiler available for building new tools. That was what was going on there. But now Clang has done a huge push with Microsoft to try and make their compiler totally compatible with Microsoft code. And if I'm not mistaken, like Microsoft's even starting to adopt it in a few projects too.
Yeah, they essentially want unified tuples and whatever LLVM's output languages, I forget what it's called, so that you can have truly universal Windows apps in a sense, or also like Xamarin and things like that when you're developing for Android. Serica 2009 Android and Visual Studio was like this horrifying process of just even getting those things usable. So now effectively like that's the pipe for plugging your code via Visual Studio on Android or iOS, presumably.
Yeah, and it's fantastic that they're doing that amount of work too.
Yeah, like right, they're making some pretty cool moves.
So, fun bit of history. So, back to history of Clang. So part of the reason why Clang is getting so much development from all of the big wigs of the tech industry is because, unlike the GNU compiler, it has a commercially permissible license, which means that companies like Apple, Sony, Microsoft, and Google can take the source code for Clang, write their own company-specific stuff, and they're not forced to share it with everybody. Hence why all of these companies are pouring just piles of money into this project to make this compiler even better. And that's part of the reason why, as of 2014, Clang started producing code that was more optimized and had better debug output than GNU, which was the front runner at the time. And of course, now MSVC is really starting to play the catch-up game in terms of having as many C++ standard features available as Clang does at around the same date. So it's interesting to see now there's competition in the market.
I think it's really helping out CL. Additionally, like the compiler lead for CL was talking about it. He had like some keynote speech where they were running like the Clang optimizer with Microsoft CodeGen, right? So they were like determining like if like the CL optimizer and the Clang optimizer were both like better. And he was talking about in the future he would like some super crazy flag where it runs both. And you get like, so it takes like a forever long time, but you get like retarded optimization or whatever. I guess it's like maybe I don't know, like one byte gets changed and this one instruction gets vectorized or something, but still like it's a pretty cool world now. Right?
That gives me an idea for a new talk, because I was recently reading a few articles on just-in-time optimizations in C# where adding an extra line of code makes it run faster.
Right, yeah. Okay. That sounded complicated.
Anyway, so we are now approximately an hour and 15 minutes in, so I'm going to go ahead and call it here. If any of you guys have any questions after the fact, feel free to come up and talk to me. If not, I thank you all for coming to see this presentation. If you guys have any questions, I'll be putting my email address up for you guys to send to. If you guys have any feedback, please feel free to send an email to my other email address for angry letters, which I will also be posting. And you guys can say, Cody, you suck. Please explain things better. Blah, 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 blah. Anyway, so that's it. Thank you all for coming. Have a beautiful night.